So we will start with the previous class. So in the previous class we have seen the layout design, like how the layout is designed and how are the different methods are used to design the layout. So in the previous class we have seen, like, in the layout designing, what we do is we have two methods. So one is micron method and another one is lambda method. Okay, so out of these two, in micron method, it was like all the lengths of our layout, okay, all the dimensions will be in the terms of absolute value. So absolute value means it will be such that, uh, suppose it is, we are going to draw a particular layer that is of 5 nanometer, so we will be writing 5 nanometer directly in terms of the value. Okay, so this will be in case of micron method. Okay, absolute value of dimensions we will be taking. But in case of lambda value, whatever dimensions we need to design into the layout, the different dimensions of a particular layer, we will be designing in terms of the lambda. Okay, so this lambda will be a value defined by the user, but this all the dimensions will be in proportion with the lambda only. So the dimensions will be in proportion to this lambda value, and this lambda value will be, if we are going to change the lambda value once, all the dimensions will be proportionally sorted or changed. Okay, so here the advantage and disadvantage of these two methods is, like, in case of micron method, it is more flexible. Okay, so it is more flexible. So more flexible in the sense, like, we can directly put each layer value individually. Okay, but in case of lambda rules, all the layers or all the dimensions of a particular layer will be in terms of lambda only. So once it is uh, scaled down or scaled up, all the dimensions will be respectively scaled up and down. But in case of micron, it is more flexible. Each layer we can optimize. Okay, so based on our the user requirement, in the micron method, we will be having more flexibility for our design perspective point. Okay, so another point that we can consider is, if it is more flexible, it is more optimized, then it will be area efficient. Okay, it will be an area efficient design. But in case of lambda, it will not be an area efficient, because once we have scaled one dimension, all the dimensions will be scaled down according to that. So it is not like a particular layer we should be taking it to be small, then we cannot scale that much uh, layer only. So it will be having more area point of view also. Okay, and along with that, in case of other, we can see here, in case of micron rule of layout designing, the user is having everything to design, or based on the dimensioning of the different layers, user has the power to define all the layers separately. But in case of lambda rule, there is no role of user. It is like, once we have designed a circuit, once we have designed a layout of a particular transistor, once you are going to change the lambda, all the dimensions will be changing according to that. Okay, so there is no role of user, as once the one particular transistor has been designed. So the role of user in case of lambda rule is very less. Okay, so these are the advantages and disadvantages also. Okay, so in micron, basically we go for having more efficient circuit. If we are going to have more efficient design, then we will be going for micron rule. Okay, so this was the basic analysis of the layout. So in before going for a layout design, so how we go from a circuit. So once suppose an NMOS is there. Okay, So once this NMOS is designed, once this is designed, this is called schematic. Okay, we call it schematic. Okay. So once schematic has been designed, we go for its layout design. Okay, then we will be designing its layout. We call it physical layout. Okay, we call it physical. But in between going from schematic to layout, we have another step that is called stick diagram. Okay, so we will be seeing the stick diagram, like how from going from a schematic circuit to a layout design, what is the role of this stick diagram. We will see that. Okay, so here basically, uh, once we are going to design a layout, this stick diagram are meant for capturing the topography and layer information using a simple diagram. So in the previous lecture we have seen like a layout seem to be something more complex. Okay, so there are different layers. Okay, in that different layers, one contact and poly, different layers are there, that might be a complex circuit to design, a complex physical layout design. Okay, so to simplify this layout, we do an exercise that is called stick diagram. Here what it will design is, it will give you the information, like if it is an NMOS, so a poly will be there. So a poly will be each layer will be represented by a line. Okay, so to simplify the layer information of a particular layout, we will be drawing the stick diagram. Okay, so suppose this is your polysilicon layer. Okay, this will be used for gate terminal. So a gate will be drawn by a layer, by a simple line, and this will be defining you this uh, source and drain terminal. So this will be like source and this will be drain. Say suppose drain is to be connected by particular output, then another line will be crossing it out. So this cross will be showing you the contact. Okay, similarly this drain is to be connected, source is to be connected to ground. Okay, then here a contact will be showing. So this stick diagram will basically simplify your layout design. Okay, so before going from schematic to layout, we will be going to layout by following the stick diagram step. Okay, so this will just simplify the layout designing. It will just give an overview, a simple prototype of the your layout. Okay, so we will see it, like what are the advantages and how this stick diagram is drawn for a particular circuit. Okay, so here this layout having stick diagram, this stick diagram is defined in terms of different colors. So these different layers will be defined by different lines, and these different lines will be having a particular color. So that particular color will be defining that what type of layer it is in the actual layout circuit. Okay, so it is act like an interface. It will be working as an interface between symbolic circuit and the actual layout. So in between the actual layout and symbolic circuit, this stick diagram will be uh, working as an interface in between these two. Okay. So all here does, so all components are vias. So these vias are the interconnection between two different layers. Okay, so this vias is used to connect higher level metals from the metal connection. So different layers of metals will be connected by different these vias. So these stick diagrams also used to show different components like vias and contacts and different layers. It shows relative placement of components. So how the different components are placed onto a layout, that will be showing its relative information. And it goes one step closer to layout. So once we are switching from schematic to layout, it will be just one step closer to your final layout design. It helps planning the layout and the routing, like how the routing of different terminals will be taking place. It will be providing an edge to designing a layout, complete layout, by using its basic simplified structure. So we will see, this is the an example. So like this is, suppose an inverter is there, so this is a layout of inverter. Okay, so this is the layout of inverter. In that layout, so before going for layout design, we will be having, this is your stick diagram. Okay, so here an stick diagram is uh, looks like more simpler form in terms of layout. So this layout is coming out to be a complex one. So this is your stick diagram. So in this stick diagram, one thing we can see different colors. Okay, so different colors are used to define different regions or different layers in that layout. So this is the complete layout. So if we simplify it, so this yellow line will be showing you P diffusion region. So this P diffusion region, so inside a P diffusion region, if P diffusion region is there, there will be a PMOS. Okay, terminals will be there, and this will be a gate. This is your P diffusion. So inside a P diffusion, a PMOS is designed. Okay, similarly, and inside an N diffusion, this will be represented by a green color. Okay, so this is N diffusion. This, inside this N diffusion, NMOS will be defined. So inside this P diffusion, PMOS will be defined. Okay, and this connections, this circle will be showing you the contact. So contact will be there. So here in that contact, it will be represented by black color. Okay, and this red color will be showing you the polysilicon that will be used to define the gate terminal. So gate terminal will be defined by your polysilicon layer. Okay, and the metals, whatever metals are there, these metals will be represented by blue color. Okay, so this is green, that is N diffusion region. Yellow will be your P diffusion region. This blue terminals will be showing you the contact, that will be contact, or you can say the metal layer, where we should be this is like a terminals metal, either VDD or ground. So this is your VDD, and this will be your ground, and here the input terminal, and this will be your output terminal. So these are represented by the metals. This red one is polysilicon, that will be showing you the polysilicon layer, and it will be connected to the inputs. So it is a polysilicon will be the gate terminal. Okay, and your uh, circles, like either circle or it is represented by cross sign. So cross sign will be showing you the layout, sorry, the contact terminal, uh, like how the contacts are being made. It will be shown by black color. Okay, so these are how different colors combinations are there. So suppose an inverter is there. So once we go for layout designing, okay, so we will be designing NMOS and PMOS. So in that, suppose this is your complete window. Once you will use any particular tool, either cadence or mental graphics, in that a window will be there. Inside this window, we should be designing NMOS and PMOS, and we will making the connection. So this complete window, what you are seeing, is considered to be a p-type substrate. Okay, so it will be a p-type substrate. So in that p-type substrate, what we do is, in p-type substrate we use to design the NMOS. Okay, So this complete is a p-type substrate. So we will be designing the NMOS first. So suppose we need to design an NMOS. So in that NMOS, uh, so this is your MOS. Here source and drain will be there. This is drain, this is source, and this is gate. Okay. So this is your substrate region. In that substrate, we will be designing this region, source and drain. So to design a source and drain, what we do is we take n diffusion region, because the source and drain regions are of n plus, okay, in NMOS. So n plus region, so n diffusion region, and we call it n diffusion region or n plus diffusion region based on the uh, your doping concentration. So if it is n plus diffusion region or n diffusion region, so it will be the first layer we will be depositing is n diffusion region. N diffusion region. So once we have deposited n diffusion region, inside that we will be making the connection. Before that, we will deposit polysilicon. So this will be a polysilicon layer. Okay. So this polysilicon layer, polysilicon. Okay. So, and after depositing polysilicon, this is like your gate terminal upside. This contact will be deposited. Okay. So this is how NMOS is fabricated. Okay. Design is layout. But for the PMOS, inside this P substrate, we should be depositing an N well. Okay. So before depositing the different layers of PMOS, we will be depositing an N well region. So N plus region will be deposited. Okay. So in that N plus region, we will be depositing a P diffusion. So inside the P diffusion, we will be making this polysilicon layer for the gate terminal, and then we will be making the contacts. Okay. So this is how different layers are taking place. So designing the layout directly, it is more complex. Either it is two transistors are only there, so it is looking like simpler. But once it is having large number of transistors, we will be having it's a complex view type. Okay. So to simplify that, we will be proceeding with your stick diagram analysis. Okay. So this stick diagram will be helping us to deposit different layers into layout designing, or it will just simplify the layout designing, and along with that, it will be giving you the simpler, you can say simpler form, so that we can have different placement of different transistors into that stick diagram, and after satisfying the different constraints into this stick diagram, we can proceed for the design of the actual layout. It will be making you uh, easy, so that we should not be having. So this placement and all the designing, why we do is we should be reducing the number of interconnects that we go for using different components. We are connecting different components, so we should be minimizing the number of interconnects. So these interconnects are minimum, then it will be having less number of parasitic capacitances, so it will be not affecting our the actual physical circuit into their other parameters. So like once it is having more number of parasitic capacitances, its output will be changing. If it is having less number of parasitic capacitances, it will be giving you the similar results that we have we will be analyzing with respect to the your schematic, that is schematic analysis. So while do the analysis, we do pre layout simulation and post layout simulation. Okay. So after post layout simulation is considered to be once we have designed the layout, after extracting that parameters and after extracting different parasitic capacitances, also parasitic components, we will be considering the parasitic components, and then we will be analyzing the circuit, that is called post layout simulation. So to make the relevance, or you can say the results obtained pre-layout simulation, through pre-layout simulation, and after layout simulation, that is post layout simulation, that should be having a matching results. Okay, that their results should be matching. So to match that results, we should be minimizing the number of parasitics while designing the layout. So that can be minimized by minimizing the number of layers, extra layers that we are going to use, or by reducing the interconnects requirements. Okay, so the placement of different components inside the layout is also important. So that placement we should be optimizing uh, before going for layout design. Okay, so that optimization will be taking place through stick diagram analysis. So in that stick diagram, there are different rules. So the rule number 1 is like, when two or more sticks of the same type cross or touch each other, that represents electrical contacts. Okay, so if two layers are being connected and it is crossing to each other, it will be represented by an electrical contact, like it will be like it is having a contact. Okay, so if one line is here, one line is here, it is touching to each other, so that means it is showing you the electrical contact. So that means these two lines are connected, it will be considered. When two or more sticks of different type cross or touch each other, there is no electrical contact. Okay, so one thing here you need to note it, like if two different color lines are touching each other, it will not be considered as an electrical contact. So here there is no contact. Okay, so here also it is of two different type, and there will be no electrical contact. But if electrical contact is needed, we have to show the connection explicitly. That means if there is a connection between this layer and this layer, we should be using a contact. So this will be, this black color circle will be representing the contact. So once we have deposited this contact onto this two different layer, at point where two different layers are meeting, so at that time if we are placing a contact, then only the connection between these two layers will be considered. Okay, so similarly it is having these two having no contact, no connection we call it, and these two are having connection, that is called as connected. These two will be considered as connected. So rule number 3, when a that is polysilicon crosses diffusion, it represents a transistor. So this is a rule, like diffusion region is there, so either it is a p-type diffusion or n-type diffusion. Okay, so it is a green color means it is of n-type diffusion. So this color, this green color line will be showing you like an n diffusion is there. So if n diffusion is crossing, this n diffusion is crossed by polysilicon, that means this crossing will represent a transistor. So it will be behaving like a transistor. Okay, so it is which type of transistor? Because it is n diffusion region is there, so it will be of n type, that is NMOS will be there. So once a green color line will be crossed by red color line, it will be showing an NMOS transistor. Similarly, if polysilicon line that is of red color is crossed by a yellow color line, that will be representing you the PMOS. Okay, one more thing, like if a contact is shown, then it is not a transistor. So once this is the structure, it will be behaving like a transistor, but the similar structure is there, but in at the point of junction we are having a contact, then it will not be showing you a transistor. It is not an transistor. Okay, so whenever a contact is there, that will only be showing you the contact in between two different layers. Okay, similarly the rule number 4, in CMOS, demarcation line is drawn to avoid touching of P diffusion and N diffusion. Okay, so in between these two, so if it is a P diffusion and N diffusion is there, so this N diffusion and P diffusion regions will be using demarcation line to separate these two. If these two are being separated, so we should be using a dotted line that will be and we will be